And we'll start this next chapter. So this is chapter 11, and as I was saying while we were in chapter 10 is a good chapter. It's a long chapter, but it wraps up the last of our mechanics. It's really what goes on in the world, and objects have both translation and rotation at the same time. But the next natural step here is to talk about then fluids and the mechanics associated with fluids. If you'll notice, everything we've done in these first 10 chapters, we've always said our object was kind of this solid piece that didn't have like multiple moving, and this is what a fluid is, flowing parts. In other words, let me take an example of a solid. So here's a piece of wood, and I'd say, okay, it's a solid. And what I mean by that, then, is if I were to drop it and talk about the acceleration due to gravity, like we did in our kinematics, or if we would do our dynamics and we'd have Newton's second law, or talk about its kinetic energy, we just gave this one big bulk and said this is its mass. Even when we did rotations, we said, okay, if this thing rotates, all the pieces move together and have the same angular speed. They may have different translational speed because they're at a different radius, but at least they're all locked together. All of our discussions then do not work for fluids. I mean, if I put a force on this fluid, so I'll put my hand in and push, I think you would agree that parts move differently than other parts. I bet none of the water down at the bottom even moved. And so to say that I'm going to put a force on the water and take Newton's second law and say F divided by the mass of this aquarium, that is not going to tell me the acceleration of this water. That is just not going to work. These all act individually. And so when you have something that behaves this way, where the individual parts are not hooked together, we call it a fluid. And of course, you have to think about fluids differently than solids, because again, what's nice about solids is if I were to push on this side, the whole thing moves. Now, granted, it can rotate. And so if I push here, I get both a translation and a rotation, but they're locked together, and I can one big bulk item. That does not happen at all with our fluids. So let's talk about fluids and how they behave, and that's the next two chapters. And so your author starts off with saying, well, let's look at fluids that necessarily aren't moving. Then we'll talk about fluids when they move. But we might ask, what if you have a fluid that's not moving and you put something in it? How does this fluid interact with this object? Some of them apparently float. Some of them apparently sink. Some of them are like kind of stuck in the middle. What is this fluid doing? And so your author starts off by saying, to really understand a fluid, let's look at a microscopic level. And he says, okay, a solid would look something like this, where the atoms are hooked together. And that's what I would say we've been doing for the first 10 chapters. We've been working with what we would call mechanics of solids. But when they're fluids, they can move around each other. And so your author makes a good statement, and an important statement right here. A liquid and a gas and a plasma are all fluids. I just wanted to stop there because I think sometimes people hear the word fluid and they associate it with liquids. Fluids are not liquids. Or I guess liquids are fluids. But fluid is anything that can flow. And so the atmosphere, the gas, is a fluid. The molecules are not hooked together. They can flow, they can move. If I put my hand and I push, I get basically the same effect out of these air molecules as if I put my hand in here and push. They move around each other. Now, there's things that are different between this fluid of water and this fluid of the air. So I'm not trying to say everything about air is the same as water. But I am trying to say the molecules move around each other, and it's that behavior. And so, again, notice as we talk about the physics of fluids, we're going to say this is true for the liquids and the gases. I'll even say it's true for the plasmas, but plasma's getting a little bit ahead of ourselves. If you don't know what a plasma is maybe a good example, and I think this is what your author is trying to say. He's got oxygen in this little tank here, and he says oxygen at room temperature is a gas, and the molecules bounce around. And we know that. About 20% of the molecules in this room are oxygen, and so they're bouncing around, and the other 80% is roughly nitrogen and a little bit of a bunch of other stuff. And so as they are bouncing around, if this room was extremely hot, like as hot as a candle or as hot as the surface of the sun, as they bounce around, the electrons that are orbiting the oxygens would break apart. And the electrons would separate from the nucleus. And that's what your author is trying to show here. So that's what a plasma is, and that's why I think he's got these little blue dots with these brown ones, but the idea here is it's still a fluid. And of course now they're charged, and so to really understand a plasma you have to understand about electricity, and we're not there yet, and that's where we start next semester, for those of you brave enough to go on to next semester, and we're going to do what happens when there are charges around. So for us, really what that means is, when I say a fluid, I mean either a liquid or a gas. And maybe later on, after we get into Physics 111, we'll throw in plasmas into there. But this chapter, probably not too much. Okay, so with that said then, let me go ahead and give you two new quantities. And so I'll start off here and say, okay, chapter 11, which is fluids. And these are fluids that are not in motion. And so tomorrow, well, we won't finish this today, but tomorrow we'll finish up this chapter, and then we'll talk about fluids that are in motion. But two things to get us started. One is the density. And so a new quantity called density is defined as mass per volume. And another new quantity, which we will call pressure, is force over area. Now, I'll pause here, but you might be able to kind of think why this is important, because when we did our mechanics of solids, we were interested in the whole mass of it. You probably saw me over here as I rubbed my hand through here and I put a push on it. Notice that I am not interested in the whole mass of all the water. What I'm only interested in is a small little piece of mass that maybe is right next to a small little force from my fingernail. And so instead of talking about the whole force of my hand, let me talk just a little cross-sectional area force, just maybe from my fingernail. And instead of talking about the whole mass of this water, let's talk about a small little volume, and so the mass in that small little volume. So that's why when we deal with fluids, instead of mass, we're going to really want to know about density, because the density is a small amount of mass in a small little volume, a little speck. Because this is why fluids are harder. Each speck can move independent of the other little speck. And so we're not interested in the whole mass, we're interested in the mass of a small speck. And hence density comes into play. And so that's what this first piece is. And look at over here. we're not interested in the whole force from my hand. We're interested in the force as it breaks down to little tiny pieces at that little chunk of mass. So as I rub my hand through here, it's not the force of my whole hand that I care about because they're not hooked together. This is not a solid. What I care about is that little chunk of area right there on my fingernail and how it is pushing just a little chunk of water right in front of it. And so that's why instead of talking about the whole force, I want to know how much force per area. I want to know what we're going to call the pressure of it. How much force do you get in a little small area? And so it's how much force in a little small area pushing a little small chunk of mass. And so that's why we begin our discussion of fluids by saying our focus when we deal with the physics of fluids is not so much about force, but about pressure. And not so much about mass, but density. So this is our new term and our new concept. Let me give you the equations. I'm sure you're familiar already with the symbol little m for mass and capital V for volume, so I'll leave those alone. But the symbol for density is the Greek letter rho. And so we're going to use it's not the only symbol, it's kind of the traditional one. So that's the one your author uses, that's the one I'll use. It's the most common one, so there's the density. Same thing here. The symbol for force, we've been using a lot of times, so it's F, and we'll continue to do that. Symbol for area, I don't know if we've used that since the first chapter, but here it is, capital A for area, since we use the little a for acceleration. And for better or worse, it is the capital P for pressure, which, as you know, in recent chapters, we saw a capital P for power, and we saw a lowercase p for momentum. And trying to distinguish a capital from a lowercase is kind of hard on a whiteboard. So I'll put kind of a little kindergartner thing up here and say you can see this is a capital P. But I'm not sure that helps too much because A, I won't do it all the time, and then B, we always have a capital P for power. So hopefully, if you have a question, you'll stop me and say, wait, you got a P up there. Are you talking about pressure? Or are you talking about power? Or are you talking about momentum? Fortunately, power and momentum usually don't come into play when we're dealing with our fluids. And so chances are, if we're talking about a fluid, the capital P is for pressure. All right, well, let's talk about the units then. What units would be used to measure density? And what units would be used to measure pressure? And like we did back in chapter 1, right, we think about a new concept, which leads to a formula, which leads to the units, which leads to a little discussion about what do those units mean. And I think density is pretty obvious. It's kilograms per cubic meter, and it just simply means that's how many kilograms are in 1 cubic meter. This desk is a good example of a cubic meter. It is a little more than a meter tall, a little more than a meter wide, and about a meter in this direction. And so this right here is roughly a cubic meter. And so it makes a good visual effect for the student to say, okay, this is a cubic meter. And so if I were to say water has a density of 1,000 kilograms per cubic meter, this means if this was filled with water, if I had an aquarium this size instead of that little aquarium, it would be 1,000 kilograms. And in fact, that's where your author starts this chapter by giving you a nice little chart here as he defines density and says, okay, you're going to need at different moments throughout these next 2 chapters the density of a lot of different fluids and also even solids for that matter, because although we're talking about the physics of a fluid, we'll end up putting solids. You saw me put a rock and some other objects in the fluid, so we want to know how does our fluid then interact with those solids. And so sure enough, water should be up here somewhere. Here it is. And so as I said, water. And it's interesting the way he laid out the units. I didn't notice this, but if you look up here, let me get a little laser pointer. He puts times 10 to the 3. Okay. I won't get a laser pointer. Let me just jump here. But up here, it's 1,000 kilograms per cubic meter. So he writes it as 1.000, but I think he did that so he could say you either multiply by 1,000 if you want it in kilograms per cubic meter, or you might want it in grams per milliliter. And so maybe I'll put that because we often use grams per milliliter also. Kind of depends if you're talking about something big or something small. And so just like we use meters for big distances, if you will, and we use centimeters or millimeters for short distances, we tend to say, all right, if we're talking about something big like a human or a car or this desk, let's go kilograms per cubic meter. If you're talking about a little test tube filled with a fluid, maybe we should talk about grams per milliliter. Also, this might be a good chance to say, what is a liter? Do you know what the definition of a liter is? This can become useful because you will be asked to convert back and forth. And 1 liter is defined as a cube that is 10 centimeters by 10 centimeters by 10 centimeters. So I think a better name for a liter is 1,000 cubic centimeters. See, because if I did this volume, length times width times height, this would be 1,000 cubic centimeters. And so 1 liter is 1,000 cubic centimeters. If you divide both sides by 1,000, of course over here on the right hand side you get 1 cubic centimeter, and on the other side you would get 1 milliliter. And so keep that in mind because oftentimes you will see grams per cubic centimeter. And so it's good to remember then that a cubic centimeter and a milliliter are the same thing because of the definition of a liter. And so some people, myself included, question why do we even have a unit called a liter? It's not needed. It's a volume. And we already have cubic centimeters and cubic meters. We don't need more to confuse us. So with that in mind, we'll keep it going. All right. Well, I'll keep going with these units, but I just wanted to point out and scan that we have some things that have a lot of density and some things that have very little density. And besides pointing out water, I wanted to point out mercury. You're going to see that it's going to come into play quite a bit, especially when we measure things like people's blood pressure. And we're going to be thinking about it in terms of mercury, and the density of mercury comes into play. And so 13.6 is a good number to keep in mind. It's a liquid, but it's very dense. Now, you can see here they've got other ones. I think osmium is the most dense, and I don't think they list it up here, but they do have gold and tungsten, which have roughly the same density. That's why one of the unfortunate scams of jewelry and stuff is to fill the internal parts with tungsten and just cover the out part with gold. If you hold it in your hand, you really can't tell the difference. They got the same density to them. But the other things are much lower in in density. But we got solids, we've got liquids, and we've even got gases. And maybe I better not say too much for the gases. We'll get that in the next chapter. But gases are difficult to really define what you mean by their density, because you can change that by adding pressure and squeezing them or warming them, and they just don't have a set densities. But you can say what their density is at room temperature and atmospheric pressure, and so that's what your author's trying to do, except for steam, where he points out this is the density at 100 degrees. You're not going to have steam at room temperature, so you got to get up to 100 degrees Celsius. Well, like I said, I better not spend too much time there on that chart. I know you can do that, but I do want to come over now and say a little bit about pressure. It's force per area, and this right here, newtons per square meter, is called a Pascal. And so, like a lot of our units, in honor of the great scientists working in the field, we'll call it a Pascal. So we will work with units of Pascal. And if you ever see that, then you know how to get back to your base units. It's a Newton, and of course buried inside a Newton is a kilogram and a meter. And so, since we've got a number of other P's going around, we actually give it a PA for Pascal. So that'll help a lot here. In fact, it reminds me, I'll say it, we're getting to the end. You guys are looking like maybe you're ready for the end to come. But there's a great joke. You want to hear a joke here? All right, so Einstein, Newton, and Pascal are playing hide and go seek. Do you know the game hide and go seek? It's an old game before video games. Kids went outside. You go outside and one person would hide their eyes, and they would count to some number, say to 10. And everybody else goes and hides. All right, so it's Einstein's turn to count. So Einstein goes to count. And Pascal goes, oh no, where should I go? And he sees a bush. So Pascal runs over and hides in the bush. Newton thinks about it for a while and decides to draw a box on the dirt. And stand in the box. So Einstein gets done counting and turns around and says, I found you, Newton. And Newton says, no. You found Newton in a square meter. That's Pascal. He's it this time. All right, well, I told you it was a silly joke. But at least I got you to wake up a little bit. Okay, so this then is a Pascal. And we're going to use it a lot because it has that force. Now, I bet this is not the only unit of pressure you have ever come across with. There are other ones, and if time will allow me, I'll get to those. But what your author does first here is say, all right, let's think about this fluid. Now for me, I'm just going to draw my little aquarium in here. But it's the reason I brought these bouncing BBs out here again, because I want you to keep this mental picture in mind. That what's going on here is there's a bunch of molecules bouncing around. So if I were to put something in this fluid and it floats or sinks, whatever you want to say, it's interacting with the motion of those molecules. Here's why I say that, is because let's just take a column of water. And maybe I should say a column of fluid. And so maybe this represents a depth into the fluid of H. And you look at the water that is just below it. On a microscopic level, you would say that those molecules are bouncing around, and what do? They hit the other molecules. But in particular, those molecules that are in that green box have to hit hard enough to hold up the weight of all of those molecules above them. If they did not, then gravity would pull it down. If you could kind of imagine in my aquarium that I have a green box here. That green box then has atoms hitting, or I should say molecules in this case since it's H2O, but they're hitting and they've got to support that weight. I guess they also have to keep the water from rushing in on this side and the water from rushing in on this side. And even down in the bottom, they have to keep the water from rushing in. So it is these hitting or the collision of the molecules that supplies the force, that is the pressure. And so the first thing I want to get out of here, kind of sees it in here, is see how those BBs have to hit, and in this case they're supporting the weight of this styrofoam. And I, of course, could slow them down, and I would say they're still got to support the styrofoam. They're moving slower, but they do that because there's more packed to them, so there's more of them, and they hold the weight of the styrofoam. But what I want you to see is two things here. One is conceptually. Do you see where the pressure comes from now? The pressure comes from the molecules actually moving and hitting. Because we can take the next step and then ask, okay, now that we see where the pressure is coming from, can you then give me a formula for how much pressure there is? And I would say yes. Because if I put Newton's second law up here, I would say that this big column of water is not moving. It's not going up, it's not going down. And if you look at this big column of water, and let's only talk about the forces in the vertical direction, what's pulling it down is the weight of this big column of water. What's pushing it up is the molecules right here at the top of this green box. And so I'm going to do this. I am going to write the force that I get pushing up from the green box as equal to the pressure from the green box times the area. And so plus pressure times area has to be 0. Now, since we're nearly out of time, I'll do a couple of math steps kind of quickly here. But I'm trying to figure out what would the pressure be equal to. And I'll pause right here, because this is saying that the pressure in that green box is equal to what? Well, notice I have mg over A. But let me pause. What m am I talking about? Is this the mass of me? Is this the mass of all the water in here? Is this the mass in the green box? No. What I was trying to say is this box above the green, this column right here, this weight of it being pulled down is then equal to the green box pressure pushing up. So this is the pressure in the green box, but this is the mass of all the water above it. Now, doesn't that kind of make sense conceptually? I mean, here's what you're saying. You're saying here that the pressure down here at some depth has to be equal to the weight that you got to support above you. And of course, it's a pressure, so it would be force divided by area. Now, let me keep going. Because we could replace mass with density times volume. We could replace volume right here with area times height. That really becomes useful because there's an area in the denominator. And so when I cancel them off and just rearrange the terms, I get something that I guess I'd call our first formula for our physics of fluids. And hopefully it fits with kind of a concept you already know. And that is, notice that it says here, the pressure depends on how deep you go in your fluid. You ever gone swimming in a pool or the ocean and dive down? You ever feel that on your ears? That's the water pressure pushing in. And the deeper you go, the greater the pressure. And that's exactly what this equation is saying. The deeper you go, the greater the pressure. Now remember, conceptually, hopefully it makes sense. Let me come back to the picture. Conceptually, you're saying here that these molecules got to hold up all the water above it. So if you go deeper and deeper, you have to hold up more molecules. You ever drive a car or hike up a mountain? You'll feel that same thing in your ears and you'll say your ears are popping, or flying an airplane, you'll go, my ears are popping. See, that's because you are in the atmosphere. You're in a fluid. And right now, the atmosphere here, these molecules have to hold up all the way above it. But if you go up in the mountains, there's less they have to hold up. And so there's less pressure. And so the pressure is depth dependent. Did you also notice it had nothing to do with the size of the cross-sectional area of that? I guess we're going to be out of time here for today, but we're going to see some interesting things with our fluids, and this being one of them. You'll notice that no matter what the shape of my vessel is, they're all at the same level. And that has to do with the pressure being connected to the depth. It has nothing to do with the cross-sectional area. This tube has a cross-sectional area much fatter than this tube, yet they're at the same height. This one's even angled, but yet they're at the same height. And so more of a discussion here, but I do want you to leave with this in mind. Where does the pressure come from? The molecules hitting. What is it equal to? The weight of everything above it, it's got to support, then spread out over that area. So force over area. Well, this is a good place to stop for today. So we'll quit here and pick this up tomorrow and more on fluids. Hey, welcome back, both online and in-person students here. As you know, we were doing our first non-mechanics chapter, although I guess it is mechanics, because mechanics of fluid. So it was a kind of a big change. It's chapter number 11, and I just wanted to point out that the first test was one chapter shy. In other words, we only did chapters 1 through 5 on test 1. So this test will do the same pattern. We'll start with 6 and go to 11. And so instead of going all the way to 12 as first indicated on the syllabus, I just wanted to kind of let you guys know. I sent that out on the weekly, I call that day 0. So week 4, day 0, I said, hey, we're not going to go all the way to 12. And that's good and bad. As you'll see, chapters 11 and 12 kind of go together because they're about the physics of fluids. However, as I was looking over it last night, thinking about today, I was like, well, you know, even though it splits kind of the fluids, maybe it's good, because chapter 12 you're going to see is a significant chapter. Your author tries to do some real challenging things in that one. And dealing with fluids in motion are pretty advanced and pretty complex. So we'll talk about that starting today, but I just wanted to point out that it wouldn't be on the exam, and maybe that's for the better. And so we're only going to have up to this chapter, the fluids that are at rest, the fluids that are static. So picking up where we left off, we had said this, and I had this little picture here on the board saying that if you kind of think of this box in green kind of deep down in the fluid, and I had a little mark on my aquarium here, so I was like, okay, here is my little green box here. These molecules are bouncing around, and it's the impact of those that create the pressure when you're in a fluid. And so that was the first conceptual idea I wanted to get across, is where does the pressure come from? And it comes from the impact of these little tiny molecules. So they're not very heavy, but there's lots of them, and they're actually moving pretty fast. And so this pressure can be substantial. But what is equal to, as we said, is they would have to be strong enough to hold up the weight of all the molecules that are above it. And so we went through a quick derivation and said then that the pressure would be the density of the fluid times the acceleration due to gravity times the depth. And so this was our first main equation here of this chapter that said pressure increases with depth. And of course I said you've probably noticed that whether you are going up or down the mountain, because you would be in a fluid called the atmosphere, or whether you're swimming in a pool or snorkeling in the ocean, as you go up and down, you can feel that pressure on your ears. And it gets really large as you go deeper. And of course, like I said, depends on the density. So the change in water, you don't have to go much of a height. I mean, you just dive simply 10 feet down and you'll be able to really experience that pressure. And if you don't equalize it at 10 feet, it starts to hurt. Whereas in the atmosphere, you got to go thousands of feet before you begin to kind of feel that pressure. But nonetheless, it's the same basic principle. So I thought I would start here today with a kind of a fun calculation. Your author does this. It says, what is the force on a concrete dam? And I guess it doesn't have to be concrete. It could be any kind of barrier there. But we'll just call it concrete. And the water is pushing on it. What would the total force on the dam be? Because I hope you begin to see that as you go deeper into the water, the pressure gets greater. And of course, that means more force. And so to figure out the total force on it, I guess we have to say, okay, what's the force at the top? It'll be kind of small, but then we'll have to add another layer and another layer and another layer and another layer. And it sounds like a perfect recipe for some calculus, right? Add up a bunch of pieces. So let's give it a try here. I guess I would do something like this, kind of looking at that picture. Maybe I'll put here is kind of a look at the concrete wall there. And maybe I will put a line right here to represent, okay, this is the top of the water line here. And I'm going to then do a line underneath it, and underneath that, and underneath that. In other words, I'm going to think about this water in horizontal strips. And the reason for that is I would say that there is a pressure, and that pressure changes at each depth, at each level. So if I write the definition of pressure over here, pressure being force over area, I could then rearrange it and say force is pressure times the area. Now my goal here is to get the total force on the dam, but let me just kind of take you back and just It's not a hard calculus problem, but it's still a calculus problem. So there aren't any easy calculus problems. But if I were to just take some random strip, and I'll just do, in my picture, the third one down, and say, all right, how much force do I get from that one strip? And so I will say that I am a distance down, and I'll call it at first h, but since I'm going to do some math, why don't I call that y? And I guess I am doing a little bit from the difference from a classical axis, a classical system, or I should say traditional system, you called down the negative. But let me call it a positive so that then the distance down, h, increases with pressure. So I'm going to call it y, and I'm going to call down positive. And so because of that, I would say something like this. I would say the pressure at this one strip is the density times g times y. Y being how far down is that strip. Now you see the advantage of your calculus come into play, because I know you're going to say, well, now wait a minute. When you say y, doesn't the strip have a top of the strip and a bottom of the strip? And so aren't those at different depths? So even the strip would have a variation in pressure. And I would say, yes, if you have a significant width to that strip. And that's where calculus comes in. And so let's say that the width of the strip is infinitesimally small. Well, what you would have said in your calculus, take the delta y for the size of the strip and take the limit as delta y goes to 0. And when I do that, then I can argue that this strip, in my mind, is so microscopically thin that there really isn't a difference in depth from the top to the bottom. And so when I say this is the pressure, there's only one depth. The strip is really narrow. Now, when I put the area then, the area of the strip, here's where the calculus comes in, it would be the length of the dam, and I believe your author uses the symbol L. Yeah, he does here. So he goes, okay, let's call this the length of the dam. And so the area of my strip would be L dy. And you might then say that this is a little bit of force. And so again, let me take advantage of my calculus class and say this is a little tiny bit of force. Because my goal is to get the total force on the dam. And so right now I would say I have calculated using calculus symbols the amount of force on one little strip. So to get the total, I would add up. And just to remind you of your calculus, right? This summation of delta y as the limit as delta y goes to 0 is the definition of an integral. And so when we say we're going to add a bunch of things, that means pull out our calculus, pull out our integration. Okay? And so we're going to add them up. That's, of course, why we use this symbol. I know it doesn't really look like an S, but if you imagine an S and elongate it, that was Newton's thinking. He goes, hey, this is a good conceptual idea of what we want for our symbol for a summation here. All right, well, fortunately, this is a pretty easy one to do. If our fluid doesn't change its density, and so maybe I should pause right there because liquids fit this category really well, gases do not. I brought out a model of what I will call my liquid, but here is a bunch of what I would call molecules, I'll just call them water molecules since I'm dealing with water here, and they semi-stick together so that you can kind of pour them and they can kind of cling together. They semi-hook together, and I call semi because if I shake them around, their nearest neighbor moves around, but they clump together. Gravity pulls them down. And so this is the behavior of a liquid. But notice how tight they are. So if I put pressure on them, they really don't get any tighter. Their density doesn't change. And so the density of water at the top of the dam and the density of water at the bottom of the dam is essentially the same. And so I'm going to take advantage of that and say, all right, I'm going to pull the density out in front of the integral. It's a constant. I'm going to pull G out in front. It's a constant. I'm going to pull L out in front because it's a constant, at least in my kind of perfect rectangular dam. I know a real dam probably flares out a little bit from the shape of the canyon where the dam was built. But in mine, the L is a constant. And then I just get this integral of y dy. And so then if we have the depth of the water, do they give a symbol for how deep our water is? I see an H here, and they called it average H. So I'll do that and say, I think what they're trying to do is to say from the very top to the bottom is an H. That can be confusing with here. Well, I'm going to follow suit, H. So calling H the total height of the water column, I would then be adding up here from 0 to H. I don't know if I like that symbol. Well, so I'll go with it here. But what I really wanted you to see then is now we can do an integration and we get y squared over 2 evaluated from 0 to whatever symbol you want to use for the depth of the water. I'll call it an H. And so this is a rho G, an H, rho GL, and then I would have an H squared over 2. So there would be my simple calculation to say what's the total force. And there's just, like I said, a good example of how we might do this calculation. Now, let's keep talking. I purposely used your author's picture, and your author's got some really good pictures in this fluid, so I'm going to use a lot of his pictures here, because not only does he talk about water, but then he switches over to the atmosphere. And I'm just going to say it's the same kind of physics, that there would be a pressure, and so your author says, all right, let's look at how much pressure there is, say, at the surface of the Earth. Okay, and so we'll call this then the atmosphere's pressure. But it's the same type of logic. The only difference really being here is that the weight of everything above you is not evenly spread out. And gases have a compressibility to them, and so to do this type of calculation with a gas wouldn't make sense because the density changes. However, the thought that the molecules down here at the surface of the Earth have to be moving around and supplying the pressure, and it has to be equal to the weight of everything above it, that's still valid. So I'll say the same thing. If I was looking at these group of molecules right here bouncing around, they've got to hold up all of the molecules above them. And of course, since they're a fluid, you might say, well, there's a ceiling above you. You don't have to hold up the whole atmosphere. And that's not quite true. I know that there is a ceiling above me, But because it's a fluid outside that door, they would be coming down, then they would flow in, and then they would squeeze. And so they would squeeze the ones up at top, and those would come down. So they're essentially the same thing. And so that's my point here, that whether I'm talking about a liquid or whether I'm talking about a gas, there still is what we're going to refer to as a pressure, and we'll just put a little sub A here for atmospheric pressure. And we'll say, okay, we have a pressure that we as humans are just kind of used to. We've kind of grown to this. And so if we go up the mountains, we feel it in our ears. We have less pressure. And come down the mountains, and we have more pressure. And I guess we could even go a little below sea level, but there's not many places that you can actually go below sea level, and you can't really go that far. But technically, the pressure then would increase if you were to go to Death Valley and go whatever, 282 feet, whatever it is, below sea level. And so we like to then give a number here, but also it becomes very useful. And so let's call this 1 atmosphere. Now, if you remember from yesterday, our units for pressure were in pascals. And what this means then is we have another unit that's actually quite useful called atmospheres. And so we might be switching back and forth, and I shouldn't say might, we will many times switch back and forth to this very, very convenient unit. And so I'll just remind you that a Pascal is a Newton per square meter. And so sometimes you'll get pressure in atmosphere, and you'll have to convert it over to the base units of pascals to do a calculation, because remember, if we want our units to cancel and we want to calculate things like maybe a velocity or maybe an energy, all these need to be in newtons. So we'd have to switch our atmosphere into pascals. Or sometimes we want to go from pascals to atmospheres. Anyways, this is just a way for me to point out there is other units that are very useful. And so even though atmospheres, you might say, isn't part of the metric base units, it's still quite useful. I'll give you another one that's also quite useful. 760 millimeters of mercury, sometimes called a torr. That is the atmospheric pressure, and that too is quite useful. You'll see why here in a second, and if I go ahead and go to another picture, I put here in my notes figure 15. Let's talk about pressure and atmosphere together with our liquid. And maybe start with something that looks like what we call a U-shaped tube. Or for that matter, really any tube that then has a liquid in it that it can flow back and forth. I have this one here that I've put some water with some red food coloring. But you will notice that all of them, regardless of what their shape is, are at the same level. I suppose I could even tilt it here, and you'll see that even in a tilted angle, they're all at the same level. And the reason for that is twofold. One is Newton's laws of pushing and pulling. Let's talk about the forces involved. But let me also put on the board here that the pressure has to do with the weight of the material above it. Rho g h. So if I had kind of this U-shaped tube, and let's just say the water level on the right-hand side is a little different than the water level on the left-hand side. See, if you look at a point down here, you would say, just to the right-hand side, what would the pressure be? And I would say, since it's opened here, this pressure is caused by the height of this liquid and then the atmospheric pressure. On the other side, it would be the height of this liquid and then again the atmospheric pressure. But since the height of this liquid is more on the right than the left, then I would say that this pressure ends up being higher than that one. And because it's a liquid, when one pressure is higher than the other, it's going to then flow in that direction. And so what will happen, because this pressure is higher, is it will flow. And of course, what that will do is bring this water level up to here, while this water level lowers. And see, once they get at the same level, then the pressures down here are the same, and the flowing stops. And so we like to say that if it's just open to the atmosphere, you're going to get the levels exactly the same. But if you do something a little different, and you don't let it be open to the atmosphere. Let me take this tube and put my thumb on it. And so now if I turn it, you'll see these first three are at the same level, but not the one that's trapped under my thumb. But I will say what is the same is the pressures. See, it's the pressure that pushes the fluid around. And so I want to emphasize that in the easy case where it's open to the atmosphere, it'll be at the same level. But if I do anything that is a bit more complicated, it doesn't mean the liquids will be at the same level. What will they be at? And that's what your author is trying to show you here. And I think this is supposed to be some kind of balloon, and so we've put some pressure on here. Let me draw that picture. So what I have is this piece of glass that has a liquid in it that's open to the atmosphere. So this is the left-hand side. And it goes around a tube here. And it looks like then this goes to a container that is under pressure. And here's how you want to think about this. Draw a vertical line down here at the bottom of our U-shaped tube. That's what I did here. And let's talk about the pressure here compared to the pressure there. And if the fluid is no longer flowing, we can conclude net force is zero. We could conclude that the pressure on the left and the pressure on the right are exactly the same. So over here, I would say I have atmospheric pressure plus this pressure, which is caused by rho, rho, a G, and an H. And over here, I would say I have the same pressure. And so here's going to be our little trick. We're going to look at this and say something like this, that if this fluid is the same, as you go up the same height, you're going to drop by the same amount of pressure. So if I were to draw a horizontal line right here at the level of the lower fluid, I would say these are at the same pressure. And then I could say that this pressure right here would then be atmospheric pressure times a increase of pressure due to this height. Not the whole height to the bottom of the tube, but just to right here. And that pressure is then what is equal to the pressure in this tube here. And so I would say that the pressure, I guess I shouldn't call it a tube. What was this thing, like a balloon? Little Mickey Mouse balloon or something here? Okay, so the pressure in that Mickey Mouse balloon then must be equal to the atmospheric pressure plus this rho GH. And that's really what I want you to see. I want you to come back here and say, why do we call this a distance? Why do we call it a pressure based upon distance? And see, what I would say here is the pressure in this balloon is greater than the atmospheric pressure by this much. And I could label it as a height. How much did it lift some kind of fluid? And so the density of the fluid could be used, and I could label it in terms of a height. And so we could then use height as a way to gauge pressure. How high would that pressure lift a column of? And most of the time we use mercury. Mercury is nice to use because it is a liquid and it is very dense. And so the height is not very high. And so this right here, if you use mercury, is referred to as a torr, or millimeters of mercury. And so what I'm trying to get at here is trying to get this make sense, that a nice way to measure pressure is also just how high would it lift a column of, and then usually it's mercury. And so apparently the atmospheric pressure is enough to lift, and this is a little more than 3/4 of a meter, and so the atmospheric pressure could lift up mercury about 3/4 of a meter. It could lift water about 10 meters. And then water just has a different density. Yeah.
So you're saying like those two they have the same pressure?
Okay. Yes. So down here, I would argue, since the fluid's not flowing, same pressure here.
But they're at different levels.
And yes, because the total pressure comes from not just the fluid, but the stuff above it.
But you would say those are the same pressure?
Right here, yeah.
Okay.
And right here, yeah.
Okay.
And therefore, what I'm going to try to conclude here is to say that the air pressure in this balloon is more than the atmospheric pressure by the equivalent of this height. And that's what I'm trying to say here. The balloon pressure is equal to the atmospheric pressure plus a little bit more. And this is often referred to as a gauge pressure. How much is it above the atmospheric pressure? For example, I think that was your bike you brought in here, right? And if you get a flat on it and you put the pressure gauge on it, it says 0. Now, what that really is 0 above atmosphere. It does have the atmosphere in it. And so you're using a gauge. And what you want is that air in the tire to hold you up from the atmosphere. So you're interested in what we call a gauge pressure. How much pressure is in that tire above the atmosphere. And then what I'm trying to say is you can measure then gauge pressure, or any pressure for that matter, in a bunch of different units. In fact, on your bike tire, you're probably more used to pounds per square inch, and so maybe you fill it up to 100 psi. And then it's a force and an area. Of course, in the metric system, we'll do newtons per square meter or atmospheres. And then what I'm really trying to get at, because this for some reason is kind of hard for students to digest. What do you mean by distance? Why would you measure pressure in a distance? And that's what I'm trying to show you is if you put whatever you're trying to measure the pressure and it lifts up some mercury, you would be able to say that the pressure in this container is the atmospheric plus the distance you lifted up the mercury. And so we're going to use millimeters of mercury as kind of a standard way of measuring pressure. And then what you'll need to know is a conversion factor. So as I'm looking at this, it looks like 760 millimeters of mercury are then equal to 101,300 pascals. And that would be my conversion factor. Maybe to keep it a little simpler, why don't I divide both sides by 760? So 1 millimeter of mercury is equal to 101,300 divided by 760, about 133 pascals. And again, I'll just dwell here for a little bit because I really want to get this across to you, especially you guys in the life science, because this is used for most measurements on living tissues. Pressures in millimeters of mercury, pressures in torrs. And so again, if I had a pressure here and I hooked it up to some container that had mercury in it, and it lifted the mercury up 1 millimeter, that would tell me it is a pressure of 133 pascals, which it really isn't much pressure. So usually, we lift the mercury at about 80, 90. And in fact, what I wanted to comment here, this is a great measurement for taking like blood pressure. I'm sure you've been to the doctor and they put a little strap on your arm and they measure your blood pressure. And so when the heart pumps, pressure goes up. Is that the systolic pressure? And then diastolic when it drops down. So it goes up and down and up and down as the heart pumps and then relaxes and pumps and relaxes. And eventually the doctor or the nurse is going to give you a reading and say, okay, your blood pressure is 120/80. What do they mean by that? Well, what they mean is when your heart pumps, the high pressure, which I think is systolic pressure, is 120 millimeters of mercury. That's the unit they're using. And they don't tell you what units they're using, which is too bad, but they'll say 120. But what they're saying is 120 millimeters of mercury. And then when the heart relaxes, then the blood pressure goes down. It's still higher than the atmosphere by a small amount, and that's what the 80 is for. And so it's 80 millimeters of mercury. And so if this was your heart at the end of here, heart would pump and this would go up to 120 millimeters. And then the heart would relax and it would only be 80. And that would be the variation of your blood pressure measured in millimeters of mercury. And in fact, we could have the opposite, right? We could have something that is what we would call a vacuum. In other words, something that is lower in pressure than the atmosphere. So in this case, the atmosphere pushes the mercury this direction. And so we would say it has a negative gauge pressure. It is something lower than the atmospheric pressure. But this is my way of saying we're going to use millimeters of mercury or torr quite a bit in measuring pressures, especially in section 9 of this book. The book does a really good job in section 9 and says, let's look at the pressure in a human eye. Let's look at the pressure in the spine. Let's look at the pressure in the lungs. Let's look at the pressure in a bladder. Let's look at the blood pressure, and kind of goes through the human body and says, okay, what are some common values of all these pressures? And what you'll see is they're all listed in millimeters of mercury. And they're all listed as a gauge pressure. In other words, this is the pressure above or below atmospheric pressure. And that's really what I want to emphasize here as we start dealing with pressures and try to correlate it back for you guys into the life science. Now, let's look at a couple more pictures here. Yeah, they kind of fit together here. But hydraulics then, hydraulic brakes, hydraulic lifts, hydraulic presses are really kind of nice because what you can do on one side transmits or flows the pressure to the other side. And using that same logic that we just said right here, the pressures left and right would be equal. Let's say that this is a hydraulic lift. Let's say that there's a car sitting right here, and I want to lift the car up. Normally, you think you're going to need an enormous force to lift the car up. And I'd say, well, yes, you do need an enormous force to lift the car up. But you don't necessarily need an enormous pressure. That's worth writing out in terms of an equation. Remember that total force is pressure multiplied by total area. So if I were to come over here and say force is equal to pressure times area, I could get a very large force, not because the pressure is high, but because the area is high. And so that's the key to this hydraulic lift, or this is the key to, say, car tires. You fill up your car tires, and most people think, well, a car is pretty heavy, going to need a lot of pressure. But the reality is car tires only have a pressure 30, 35, 40 psi. Whereas I'm sure your bike's probably operating at 90 psi, 100 psi. And the difference being a bike only has 2 tires, and they're narrow, and they're really, really small. So you have a small amount of area, so you make up for it in a lot of pressure in order to hold the total weight of the bike and the rider. But a car is kind of the opposite. A car has quite a bit of area touching the ground. It's got 4 tires. They're nice and wide. They even flatten out and bulge a little bit on the ground, and you get quite a bit of area. Therefore, you only need a low pressure. And so what's really nice about hydraulics and the principle behind the hydraulic system here is that if you look in this connecting rod between these two, and so let me call this the lifting cylinder and this the master cylinder, is the pressure will be equal, or if it's not, it will be flowing. Okay, so let's say I'm not trying to lift it. Let's say I already lifted it, I'm just trying to hold it, or let's just say I'm trying to get just enough to lift it up. I would say I need to create enough pressure in the master cylinder to then match the pressure in the lifting cylinder. See, I don't have to match the force, I have to match the pressure. And so if I come over here and follow up with the math and say, okay, so the pressure in the master cylinder and the pressure in the lifting cylinder are the same. That means in the master cylinder I have to apply a force F over an area of area 1. That has to equal to force 2 over area 2. And this is what we would call a mechanical advantage. That is, this same pressure spread out over a much bigger area is more force than the same pressure over a little bit of area. And so when I rearrange the math here, I can say force number 2. So the amount of force on my lifting cylinder is then A2 over A1 times the force that I apply to my master cylinder. So on my master cylinder here, I could apply really a small amount of force, but it gets amplified by the ratio of area 2 to area 1. And so I might only need to push with my hand here. Or I can just take a hand pump And then the hydraulic fluid flows through and lifts up the weight of the whole car. Or even then, I don't even need a hand pump. Maybe I'll just hook it to a little compressor. The compressor's maybe running at 30 psi. And I've got 30 psi, but I'm lifting up an entire car because of this added ratio. In fact, your author gives you a good, most common, I think, hydraulic system that most people know, and that's just in your brakes of your car. And there's a couple of mechanical advantages here, and they're showing here somebody's foot, and they apply a force of 100 newtons. It's not much of a force. But because the brake pedal has a pivot here, and you've got different lever arms, the force going into the master cylinder here is actually much greater just because of, well, that'll take us 2 chapters ago, to our lever arms. And so again, that amplifies the force just because of the torques involved. And then, of course, this is a small area. The fluid flows through the hydraulic system of our brakes and gets to a bigger area. And again, that amplifies it through a hydraulic system. And so between a lever system and a hydraulic system, the amount of force being applied to our brakes is enormous. And of course, then somebody can just step on the brake and stop an entire car. A big, heavy car. And so that's our idea here of our hydraulic system. All right, well, let's keep moving on. There's, like I said, a lot of neat things here about the behavior of fluids, even if they're not moving. Now, I should be a little careful here. Obviously, the hydraulic system, they have to move a little bit, but at an equilibrium, we could do the calculations to figure out how much the force gets amplified. All right, well, your author then says, well, let's look at some other nice things. Here's, by the way, the conversion factor. And it was discovered by Archimedes, so it's called Archimedes' principle here. And I'll go ahead and try to draw the same picture that your author has. But maybe you felt this. This is kind of the thinking in Archimedes' day. And Archimedes was lowering himself into a bathtub. And he had some other scientific thoughts on his mind. But taking a rock, and of course I want to emphasize anything, it's not just a rock, but when you submerge it underwater, did you notice the scale went down? Let me pull it out of the water again. So if I were to do a free body diagram here, which I will in a second, I will come to the conclusion that the weight of this rock looks like 17.5. But when I put it underwater, the scale reads about 11. Does that mean the rock weighs less? No. It's really no difference than this, and this is Archimedes' genius. He says, well, if you were to push your finger, it would read less too. That doesn't mean the rock weighs less. It just means something else besides the scale is lifting up on it. And so Archimedes realizes there must be somehow these molecules in the water, and for that matter any fluid, have this lifting ability. We're going to call that a buoyant force. We're going to say water or any fluid can actually lift things up. I'll draw it this way. Let's say without water. Or maybe I should be a little more general and say without a fluid. If I were to draw a free body diagram, it would look something like this. Here's the rock, and I guess I would be pulled down by gravity, mg, and then it would be lifted up by the scale. Let me just call it the tension in the string. And if you're just holding it there, you would add up these forces and say, let's add up the forces in the y direction. You would have tension up, you would have mg down. You would say that has to equal to ma, but you would also say A would be 0 for that case, because you're just holding it. And so then you would say the tension is mg, and the tension then would be what is read on the scale. The scale is reading how much somebody's pulling on it. Yeah.
I just want to make sure I understand this correctly. So the reason why that's happening is because the weight that's being displaced is greater than the weight of the rock. Buoyant forces.
Well, I tell you what, let me keep talking. All right? Because that's exactly what I want you to get. I want you to understand why the reading on the scale is less. And I want you to understand why it is reading less. Not only why is it reading less, but we could calculate how much it is reading less. And that's what Archimedes is after. And so here's Archimedes' thinking. Archimedes' thinking is, okay, when you hold it out of the water, or out of the fluid, you have this scenario. And so the reading on the scale is exactly the weight of the rock. But if you are in the water, and so in the fluid, then you have this rock. You would still be pulled down by the same amount, right? The gravity didn't get less. It's still that, if you remember back to chapter 6, it's still the gravitational constant times the mass of the rock times the mass of the earth divided by the radius of the earth squared. So it's still being pulled down. It didn't magically disappear. But what I'm trying to get you to see is just like my hand pushing up here, there must be some kind of mechanism, and that's what I want to talk about. The water must be doing something and must be lifting up. So I'm going to say that there is then two upward forces. There is still the tension on this scale, but then there is what I'm going to call F sub B for buoyant force. And this is a kind of the first step. It's more of a conceptual step to say there's something about the water that we want to study a little deeper. There's something that the fluid is doing that is supplying a force similar to my hand. Because if we did the mathematics here, we would say the sum of the forces in the y direction, and we would have tension going up, we would have buoyant force going up, we would have mg going down. That would have to equal ma, and if we're just holding it, A would be 0, and so the tension and the reading then would be mg minus the buoyant force. And so what I want to emphasize is when I put it under the water, it doesn't weigh less, it reads less. Do you see the difference? The reading on the scale is less. Again, it's no different than doing this. I hold it out here, and when I put my hand underneath, and now it says 11, it's not like the rock only weighs 11 now. It just reads 11 because the combination of this pushing up and my hand pushing up equals what pushes down. And so again, the rock really is 17 and a half, which means if I lift it up till it says 11, it means the scale's pushing up with 11, and so my hand must be 6 and a half to get a total of 17 and a half upward. And so again, step number 1 is just to say, there's something going on in this water. Somehow the water is lifting up. Let's refer to that as a buoyant force. And in this case, I actually measured the buoyant force, right? Because I got a reading back here of 17 and a half. And then when I put it under the water, I got a reading of 11. So if this is 11, and this is 17 and a half, the buoyant force must be that difference of 6 and a half. All right, so clearly I've measured that buoyant force. And the lab we're going to do today is exactly this. You're going to measure that buoyant force. And that's exactly how you're going to measure it. You're going to first weigh it out of the fluid, and then you're going to weigh it in the fluid, and you're going to take that difference and say, that is the buoyant force. That's where the buoyant force. Now, we might then take this one step further, and that's what Archimedes did. So the first thing is Archimedes realizes, getting into a bathtub, that there must be some kind of upward force on him from the water. By the way, did you notice that the rock still sinks? I mean, I guess I didn't put the rock in here. I did that yesterday. But I'm not saying that the rock floats. I'll let the rock go. It clearly sinks. But the water is still pushing upward on the rock. Whether something sinks or not, there is a buoyant force on it. And of course, it would sink if the buoyant force was not enough to overcome the weight. That's the difference. Something underwater is still lifted up. It's just not lifted up enough to overcome the weight of that object. Where other things do float. And so clearly, if I put this underwater and let it go, then I would say the buoyant force was more than its weight, and that's why it got pushed up to the top. And so Archimedes starts this thinking process, and it goes something like this. And so let me take the aquarium again. Now let me take this object underwater, and to make it easy on me, I'm going to make a cube. In fact, I'm going to make it even easier and just think in 2 dimensions and just make a square. But if you remember, the pressure underneath this box is greater than the pressure on top of the box. Well, maybe that's worth putting up here on the board again. We started today with this formula. Pressure is the density times G times how deep you are in the fluid. And so I would make this argument that it's actually the pressure, and you might say the net pressure, that is lifting it up. Because down here, if I wanted to put the force from the water lifting up on the box, and so I'll say the force upward on the box would be the pressure times the area. And then over here, at the top of the box, the water would be pushing down on it. So I would say force down is pressure times area. But do you see how this pressure at the top of the box is a smaller number than the pressure at the bottom of the box? And so the lifting of this box is really caused by that pressure differential. How much is the pressure under the box compared to the top of the box? So maybe I will put here pressure at bottom of box, because that's the one that pushes up. And over here I'll put pressure at top. I tried to make my calculation easy by saying it's a square, so the areas are the same, or it's a cube, so the areas are the same. But then I would say that if I were to take the force pushing up minus the force pushing down, the difference between those is, and there it is, the buoyant force. And so I'm trying to give you a reason for that buoyant force. Hopefully you see there was a buoyant force. Now hopefully you're seeing the reason why there's a buoyant force. Now let's take the last step and calculate what would be the value of that buoyant force. And that's the Archimedes principle. Archimedes puts this together and says, okay, the force going up would be pressure at the bottom times area, and then pressure at the top times area. If you factored out the areas, you would then have the pressure at the bottom minus the pressure at the top. If you put in this nice little equation right here for the pressure, you would have rho G, and I will call H at the bottom of it. And then I will have a rho G H at the top. You might even then notice that each term has a rho and a G. So this would be the difference between the bottom and the top, which the difference between the bottom and the top, wouldn't that be the height of the box? Isn't this then that difference? And I'll do you one better. If that's the height of the box and you multiply it by this area, that area is this right here. Because this is where the pressure was pushing down. So if I take this area and I multiply it by this difference, isn't that the volume of the box? And so let me write it just like that. Let me write this as the volume of the box. So I'll put volume of the box by putting this and this together. And then I will say density, and then I will say G. Now remember, this is equal to the buoyant force. So keep in mind what I'm trying to do here. I'm trying to say, A, there is a buoyant force. B, it is caused because of the pressure difference. And then C, I'm trying to give you an equation. I'm trying to give you a way to calculate how much buoyant force there is. If you put something underwater, we can now calculate it. And I'll take some more steps here. Because remember what density is? Density is mass per volume. So if you go density times volume, what are you going to get? Mass. But a little warning right here. Which mass? Is this the mass of me? Is it the mass of the whole aquarium? Is it the mass of the rock in the aquarium? And that's the common mistake. Thinking it's the mass of the rock of in the aquarium, or whatever object you put in. See, this is the volume of the box. But what's this right here? This is the density of what? Yeah, this comes all the way back to the pressure. So if you'll let me do this, I'm going to put an F sub L here to help us remember that we're talking about the density of the fluid. Because I would say if there's anything hard about Archimedes' principle, it's this. You are putting an object in a fluid. And so keeping track of, are you talking about the density of the object or the density of the fluid? Are you talking about the volume of the object or the volume of the fluid? What are you talking about? And so this is my first warning, and I have a feeling I will have to say this warning many, many times. Do not confuse which density we're working with. Very easy to do, because when you put the rock in the water, you are going to ask this question. Are you talking about the density of the rock, or are you talking about the density of the fluid? And that's a great question, because now, can I really put those together? Because aren't they different things? If I'm careful, yes, I can put them together. Let's do this. This right here, as you're pointing out, is really not the volume of the fluid. And a good catch. You're nervous about putting those together because you would think that they have to be the same thing, either the object or the fluid. And I've got them mixed. But I could do this. I could say, if I look at this rock completely underwater here, the volume of that rock is the same as the volume of water that used to be there before I put the rock there. So I'm going to call that a displaced water. In today's language, we'd probably call that missing. But in Archimedes' times, you didn't, misplace your phone. You displaced your phone. Okay, so when something is missing, we're going to call it displaced. So let me call this displaced volume of water or of the fluid. So I'm going to then put volume, and I'll just put DISP for displaced. I'll even put underneath it, it's the displaced fluid. Because when I think of it that way, then I have mass. And what would you call mass times G? Isn't that weight? And so I'm going to call this weight. But let me be careful here. Weight of what? Is it the weight of the object? It's the weight of the displaced water. And I want to keep using that word displaced, or maybe I should say displaced fluid, because I want to emphasize this is not the weight of all the water in the aquarium. It is not the weight of the object. It is the weight of the water that would be here if the rock wasn't here. So if I take the rock out, if you can kind of imagine that same volume of water, that's what the buoyant force is equal to. It might be a little easier to see without the rock, and I put the piece of wood in there because the wood is more rectangular. And so if I submerge this all the way under here, I would say that the volume of this piece of wood is displacing so much water. And the weight of the water that would have been there, the weight of the water displaced, is the buoyant force. In fact, Archimedes argued it conceptually and just said, if you were to draw that object and remove it, you would now have water there. And that chunk of water is not going up or down, meaning nature designed the pressure around it to support its own water. And so he concludes that the buoyant force is equal to the weight of the fluid displaced. So I'll point out Archimedes' words, but I want to give you it in terms of an equation. Here is what he says. It says, according to the principle of buoyant force, on an on an object equals its weight in the fluid. It equals the weight of the fluid it displaces. So the buoyant force is equal to the weight of the fluid it displaces. Which really explains why some things sink and some things float. If I were to put this in the aquarium and let it go, it ends up sinking because gravity is pulling it down, but the buoyant force is lifting it up. Which one's stronger? Well, apparently in this case, the weight of the object, and it sinks. But for this, if I put this down here, which is stronger, the buoyant force or the weight? Well, obviously the buoyant force, because it pushed it up. And here's something interesting. Watch when it starts to float. when it's floating, do you see that it now is displacing less water? See, what I would say is when it is fully submerged, the buoyant force is more than its weight. And that's why it gets pushed up. But remember, excuse me, the buoyant force is equal to the weight of the water it displaces. So as it starts to break the surface, we now displace less water. That means the buoyant force goes down and down and down. And eventually we reach equilibrium. So then the buoyant force must be equal to the weight of the object. Here's kind of what I'm getting at here. If we're looking at something that sinks, that means it is fully submerged and underwater and down on the bottom. But if we're looking at something that floats, that means the water that we displace is not the same as the volume of the object. Did you catch that? Maybe this is worth repeating here and drawing a picture. Because I want to apply Archimedes' principle to these two scenarios. Something that is completely submerged versus something that is floating. And even though they both are part of Archimedes' principles, because one is submerged and one is not, they have kind of a different behavior, a different flavor, if you will. And so let's talk about something that sinks. So if something sinks here, I will say it's sitting on the bottom of the aquarium. And if I do a free body diagram here, I would say it's being pulled down by its weight, mg. It's being lifted up by a buoyant force. That's our Archimedes principle. It's also being pushed up by a normal force if it's sitting on the bottom, or in the case that I was showing you earlier, I had a string attached to it. There would be a tension pulling it up. And I would get something that would look like this. Normal force pushing up, buoyant force pushing up, must equal weight pushing down. And of course, where it's different is over here if it is floating. If it is floating, then notice that only part of the object is submerged. And if I do a free body diagram, I would say gravity is pushing it down and the buoyant force is pushing it up, and there are no other forces. That's the big difference. It's not hitting the bottom or it doesn't have something else on it. And so for this sinking case, I would say mg minus the buoyant force is the normal. In other words, if there was an underwater scale down there sitting on the bottom, that normal would be the reading on the scale. You might call it its apparent weight, and that's what your author says. If you were to be underwater and put it on a scale, this would be its apparent weight. And for it to sink, notice for it to sink that this term has to be greater than that term. Now, let's do a little math here, because here's where I really want to warn you about mixing up the object and the fluid. So, what's this one right here? mg, this is the mass of what? The object. So let me put m and I'll put an OB here for the object. Because this is the buoyant force. And what did we just learn that Archimedes discovered? The buoyant force is equal to what? The weight of the fluid displaced. So how do you calculate weights? Well, I guess it's mg. But here's what I want to be careful. What m is this? Yeah, the fluid or the water that has been displaced. So maybe I should put an FL here. And so that would be the normal. But let me keep going with this. Let me use density, because right here I would say I could replace mass with density times volume. But again, let me be careful. Density of what? Object. Volume of what? Object. So the density and the volume of the object go together, and then what would this be here? The mass of the fluid would be density of fluid times volume what? Is it the volume of all the water in the aquarium? Just the stuff displaced, right. So maybe I should put displaced here. Yeah.
Are we ever talking about the total volume of the fluids, or is it easy? So you could just say volume fluid and you just assume that they're not.
Right. Good point. I could put volume fluid here because we're never going to be concerned about the whole volume of the whole thing. This is just my silly way of trying to say you can see a recipe for disaster here if you mix up the object and the fluid. And students do that a lot. That's probably trial and error. That's hopefully what you'll straighten out before the test comes on Monday. Right. But watch this for a moment. And I guess I've kind of run out of room, so I'll continue my calculation over here. Remember, I'm talking about the scenario where it actually sinks. It's completely underwater. So in that case, what would you say about the volume of the object and the volume displaced? They're one and the same. And so I know it sounds ridiculous that I made such a big deal out of them and then they're the same. Well, they are if they're underwater. Completely underwater they are. That's going to change over here when we talk about something floating. So my logic is going to be the same, but I'm not going to be able to say that the volume displaced and the volume of the object is the same. And I did want to make sure you don't confuse the density of the object with the density of the fluid. So if I take the idea that the volume is the same, I can pull it out, and I'm not even sure what to call it. Maybe I'll just call volume of the objects. But again, I just want to be careful that it's also including the volume being displaced, at least for the case where it's underwater. And I also want you to see this. This would be the density of the object minus the density of the fluid. And so after going through all of our forces and Archimedes' principle, we come up with an answer to when is something going to sink and when is something going to float. And do you see it all boils down ultimately to this question: how do the densities of the two compare? If your object has a greater density than the fluid, it will go down and you will need a positive normal force lifting it up. If your fluid was at a greater density than the object, it would want to go up, and the only way to keep it down on the ground underwater is to have a negative normal force pulling it down and keeping it down on the bottom. And so I don't want to use the phrase that sometimes I hear people say, oh, things sink and float because of their density comparison. That's not why they float or sink. They float or sink based on the forces. The forces are then ultimately connected to their density. And so anything that has a density greater than the fluid it is in, it will sink. And most of the time our fluids are water and the density is 1. So if I were to put something in here with a density greater than 1, like I already did, the rock, it would sink. And so rocks sink. Anything with a density greater than 1. I think I've got some brass here. I can put the brass in here. It sinks. What's fun to kind of watch though, and I guess you already saw it because I put it in there yesterday, is this piece of wood. It's a high dense mahogany wood. And now that it's all wet, it may not look like a piece of wood. Most people think wood floats, but it doesn't float just because it's magically wood. It floats because it has a lower density than 1. And so if I have a high density piece of wood and I put it in here, it ends up sinking. So most woods have a density less than 1. So most woods float, but not all of them. Most rocks have a density greater than 1, so most rocks sink, but not all rocks. Here's my volcanic rock. And it has a density less than 1. And so it floats. And so it's not so much about whether it's made out of rock material or wood material. It's about the forces, which come back down to the densities. And of course, something that has a density exactly 1, and this was our attempt to get it exactly 1, and then it rusted and air leaked out. So we're not quite at 1, but this is pretty close. It's a hair less than 1. And if I let it go, you'll see it does actually float. It is a hair less than 1, but barely. In fact, now that I have some floating objects in here, let's come back over here and let's do some math here with things that float. Because I want you to see my logic is still the same. And so I'm going to come over here and say, well, the buoyant force is equal to the weight. And there aren't any other forces. It's not sitting on the bottom. It doesn't have a scale or anything other than like over here with a normal force. And the buoyant force, let's run through it again. What does Archimedes' principle say? The buoyant force is equal to what? The weight of the displaced fluid. So what I'm going to do over here is put mg, but I'm going to pause like I did back here and ask you, which m is this? This is m of what? This is m of what? Yeah, okay, so buoyant force would go with the mass of the fluid being displaced. And then this is the weight of the object pulling it down, so I'll put an OB there. And then I'll do like I did over here. I'm going to replace mass with density times volume. So this would be density times volume times G has to equal density times volume times G. But I'm going to take this as the same little warning. Let's be careful here. What density is this? What volume is this? What density is this? What volume is this? So this is the fluid displaced, right? So I'll put a little FL here for fluid. And over here, I'll put volume and I'll put an FL, but I'll even put out, again, displaced. Because, again, as you pointed out, I don't want you to think it's the volume of the whole aquarium, but we never do that anyways. But I do want to talk about the volume displaced in a second, but let me finish over here. This would be the density of the object and the volume of the object. Now, fortunately, the G's are the same. But here's my question for you. Is the volume displaced the same as the volume of the object? Not this time. See, it was last time because the whole thing was underwater. And so the volume being displaced and the volume of the object were one and the same. But here, when something's floating, the whole idea of floating means part of it is above the water. And so for this piece of wood, it kind of looks like maybe 2/3 of the volume is underwater. And so the volume displaced is only 2/3 of the volume of the object. And it looks like this little metal sphere that I tried to make a perfect balance. Boy, the amount above the water is something like 1%. So they're almost the same volume, but not quite. And this floating rock, I don't know, maybe is more like 90% underwater and 10% above the water. And maybe something a little different is more out of the water than in the water. But I'll say it again, anything that floats means that the volume displaced is less than the volume of the object. So I am not going to be able to say that these two are the same volumes. But I could do this. I could write this a little different and put volume of the fluid displaced divided by the volume of the object would be the same as the density of the object over the density of the fluid. And so here's a nice another equation that we could use to figure out then how much is, say, underwater. Because isn't that what this means? Isn't this the percentage that's underwater? The volume displaced over the total volume of the object? So I would describe this quotient right here as how much is actually underwater. And then I can get that from the ratio of the densities. And styrofoam, as you can see in this, and it might be hitting the rock a little bit, but you can see it's barely underwater. Something like 10% is underwater. And so I guess I would say styrofoam has only 10% the density of water. Whereas this, 99% of it was underwater. So this must have a density very close to water. Less than water, but 99% that of water. And so we can kind of get that ratio, yeah.
For like styrofoam, since it has so many holes, if it were like soap, would that like change everything?
Yeah. And I was going to say you could think of it in a couple of different ways, but maybe the easiest way, I think how you were thinking of it, is if those little air pockets had water in it, then I would think of this as a heavier object, same volume, so its density is higher, and it would be lower under the water. Yeah. And so wet styrofoam thinks a little different, or maybe if you've ever had a surfboard that gets a nick or a scratch and then soaks in water, surfboard just doesn't work well anymore. It just kind of sinks in the water. Yeah.
I think the rock did that because the rock has like a ton of holes, so it seemed like it was floating really well in the beginning, and then as it more and more filled with water, it's lower.
And it might, and the rock does. That's why this rock ends up with a low density, because it's got a lot of air pockets in it. Yeah. All right.
What would you do for something like, I guess the only thing I could think of would be like a towel if you were to place it, and then eventually it would become obviously a lot heavier, and let's say it were to sink, how would you, so if it were to initially float and then finally get down to the bottom, how would you approach?
Well, I guess I would, while it's floating, I would be doing this. And while it's floating and soaking up water, I guess I would be saying the density of the object is getting bigger. So the percentage underwater is getting bigger. And so it's getting lower in the water as it's soaking it up. Eventually, though, if it becomes greater than the density of the fluid, it ends up sinking. And I can't use this information anymore. I would have to run over to here. And so now it would sink. And I would say now that it's sitting on the bottom would be lifting up with a normal force that is based upon how much more is the density of the object compared to the density of the fluid. And who knows, it might still continue to soak up more water while it's in the bottom, so the normal force would keep going up and up as the density of the object keeps going up and up. Well, I hope I didn't spend too much time on Archimedes' principle there, because we've got some really other neat things to talk about here. Maybe it would be a good time for a break. So why don't we take our break now, and we'll continue the rest of the chapter when we come back in 15 minutes. All right, so come back at quarter till. All right, hey, welcome back here from the break. Good to see all you guys back here, and you two online. Let's continue where we left off, and I do want to do one more thing, since you guys asked some really good questions before we went to the break. You were talking about this rock soaking up water, and I then go, you know what? I've got this, we call it the Cartesian diver. It's got a clear bottle with some clear liquid, so it's a little hard to see. So I put some red tape on a test tube. I don't know, can you see the test tube, the top of the test tube, the bottom? It's actually upside down. Can you see there's a pocket of air trapped in the test tube? See, and can you see the test tube kind of floats right now? But watch what happens when I squeeze the bottle. Let go of the bottle. You see right now a combination of the glass of the test tube and the fact that the test tube's half filled with water and then half filled with air. The density right now is a little bit less than the density of water, which is 1 gram per cubic centimeter. And it floats. But if I were to apply pressure to it, I could squeeze the air bubble, essentially then giving more water into it, thereby raising the density, thereby making it greater than 1 gram per cubic centimeter, and therefore sinking. And so if I grab the plastic bottle and squeeze, it now sinks. Let it go, it floats. And of course this one is designed with a little air pump, so I can actually pump it. And if you look every pump, you'll see the little air get smaller. There we go. And now the density is greater than 1. And so it sinks. And if I let the pressure out, it floats. And so there was, I think, kind of your statement here about in being greater or less than the density of it. Here's a fun one for discussion. These beads, I've got white beads, I've got blue beads, but would you say they float, or would you say they sink, or neither? And I hope you see there's a fluid under here. I'll shake it around. But there's a fluid above it. And so maybe it's stuck in the middle? It's actually pretty ingenious. I'll shake it up and let it settle. And you'll see the white beads float and the blue ones sink. But if you watch it for a while, you'll see them meet. And it is pretty clever. The liquids in here are plural, liquids. There's an alcohol and a salt water. The salt water is more dense, so it sinks. In fact, the salt water is more dense than not only the alcohol, but also the white and blue beads. The alcohol is less dense than both the beads, so it floats. So the beads sink in the alcohol, float in the salt water. And that's a little trick. When you mix it up, you get a combination of alcohol and salt water, which happens to have a density between the two beads. And the blue ones then sink in this mixture because they're greater density than the mixture, and the white ones float in the mixture. But with time, the alcohol floats to the top and the salt water sinks to the bottom, and eventually they meet in the middle. And so that's not really something new, that they're just in the middle. It really is, they sink and they float, depending on which fluid we're looking at. And we deliberately made two colorless liquids so they would look like one liquid, and it would look like it would be kind of in the middle. So it's a fun little experiment because of that. Well, there's a couple more pieces to this chapter, and then we'll call it quits for chapter 11, and then we'll move into chapter 12, which, as I said at the beginning and we'll repeat now, your exam will only go to end of chapter 11. And so right here where we're going to end, and that's, I think, probably good, because I know that you're going to then spend the next 6 days getting ready from chapters 6 through 11 and focusing on those, even though we will go to chapter 12 and then 13 tomorrow here. But let's talk a little bit more about our fluids, and in case our fluids at rest, and let's look at what we call cohesive forces and also adhesive forces. And kind of the best way I can demonstrate this is to come back to my little contraption that I call my fluid. And so these balls that are supposed to represent the molecules in a liquid are my way of showing I can pour it, and I can shake it, and I can stir it. But it's also my way of showing, notice that they stick together a little bit. And so if this was water, I would say one H2O molecule wants to stick to another one. Like kind, that's a cohesion. And so there is an interaction between their own molecules, cohesion. But also, and not really shown well on here, these molecules will want to stick to the glass surface here. And so there's an interaction, and that's an adhesion. Okay? And let's start with the cohesion for a moment. If I were to take this liquid and kind of pour it out, so it's kind of a thin surface here, and I try to pull it apart, it's going to take a force. It's going to take some effort. They want to stick together. They have a cohesion. And for me to actually then break them apart takes an effort. Your author gives a really good picture of an experiment actually doing this. He's got this figure here, where there's a little metal wire, and you put some of the fluid in here, and you pull on it with a force F. And if you pull enough, you'll eventually tear that fluid. Now, I say tear, that's kind of a terrible word. It almost sounds like it's damaged. But I do want you to get the idea that you're actually separating in them. There is a cohesion of them. So in other words, these want to be stuck together. And so we call this a surface tension. For you to actually then go from the air into this fluid. So for me to actually go into this fluid, I've got to rip open those molecules. Now obviously it might not take too much effort, because I can just do this and I can punch a hole in it. But this is referred to as a tension, a surface tension. It's the idea of separating them. And so this breaks that tension. It takes an effort to break the surface apart. And this experiment is one to measure what is the strength of it. And so they are pulling and breaking it apart. Let me try to draw a kind of a side view of this. If the water or soap, whatever this is clinging to here and clinging to here, and I stretch it, then I would have a cross-sectional view of a fluid that might look something like this. I'll make a sad attempt to try to make this a three-dimensional picture. But this going back is supposed to be this little wire here, and so my fluid kind of thins out as I try to pull it apart. And so we could then define a surface tension here by saying, well, how much effort does it take to pull this fluid apart? And we like to then say that if this is the force F that you needed to break it, and that holding it together is spread over the length of it, and there's really a top surface and a bottom surface, we could say this. We could define something called gamma, the surface tension. We could say this is the force divided by, and in this case I'll say 2L. In other words, what gamma is a measurement of how much strength do you get from your one surface per one length. And so notice I have taken the amount of force it needs to break it, and then dividing it by the number of surfaces, and also dividing it by the length of that surface. Did you catch that? And so this gamma factor, called the surface tension, is actually then a measurement of saying, okay, how much strength do you get per unit length for each surface? Because you might have more than one surface. And this little experiment is kind of showing it. I guess a good definition for gamma, which is the surface tension, would be force per length. I like to say it's not only force per length, it's force per length for each surface. And so this little experiment has a front and a back here, or a top and a bottom. And so it's going to tear right here and tear right here as I pull that. And so each little fluid has its own value. And your author gives you some of these values. And so note that if I go to the little chart, and as you do the homework, you're going to have to look at some of these and say, okay, how much tension do I get? And so you'll look up, well, I am working with, say, soapy water. And so here's my gamma factor. And then if you multiply that surface tension by how much length you have and how many surfaces you have, you can figure out what's holding it together. So that being said, your author says, let's look at, say, little tiny bubbles. Actually, I wrote in my notes here that there's another picture worth looking at. Oh, yeah, right here. Given that you guys are in the life science here, you might appreciate little tiny bugs that can walk on the water. And this is why. I certainly couldn't put my whole hand on here and try to push myself up on the water. The surface tension isn't that strong. But it is strong enough to maybe support something that doesn't have much weight. And so there are bugs, and this is supposed to be a leg here showing that if you are holding up the weight of this bug, pulling down, the surface would look something like this. And you would have, here's the surface of the water, then here's where the leg comes in like this. And so the leg or the foot is kind of here, going up for the bug. But if I draw then a free body diagram here, you'll see, so here's kind of the foot. I've got weight pulling it down, but I've got a tension pulling it on each side. Now, of course, there might be some kind of angle made here. But I would then say something to this effect, that if this is the surface tension pulling on it, T sine theta is pulling up. And I guess the other side. But that's kind of a two-dimensional view. You might say then there's a circumference around this leg. And so if I look at how much force total is pulling up at an angle, so I'll go F sine theta, this is where this surface tension becomes really nice. I could say that if I take gamma and multiply by the length, and so I'm just going to kind of assume that the foot of this bug is going to make a circle, so it would be a circumference. So this would be 2 pi r. And then sine theta. That would be the total force lifting up. And then that would equal to the weight if it's supporting. And clearly, we are limited in this number and the radius of the foot and the angle. And so if this number can't be big enough, well, then you can't support the weight of that bug, and that's what would happen if I or you or a dog or a cat tried to walk on water. We just couldn't get enough force from the surface tension to support our weight. But a small little bug could. Now, your author says, let's look at kind of circular things. That's why I brought out the soap bubbles here. And so what if I were to make then a soap bubble? Oops. Try that again. And so if I make a soap bubble, maybe another one higher up. But I might ask this question, what is the gauge pressure in there? See, the surface of that is pulling in, it's contracting in, and I guess it would look something like this if I tried to draw a picture of it. Let's see, what does a sphere look like on a board here? Maybe I'll start with a circle and then maybe draw an equator. And I would say then right here at the equator, the surface tension's pulling in, but the air inside of here is pushing back. And so eventually those will balance and we'll have a bubble, and that will determine the size and the pressure of our bubble here. And so if you stand back here and say, all right, what is pushing, say, the top half off? I would say it is pressure times area, where P is the pressure in the bubble And the area would be pi r squared. And so I'm pushing the top hemisphere up. Okay, so what is holding the top hemisphere on? Well, surface tension. So I'm going to take gamma, so there's the surface tension, and multiply it by the area that is connecting, and so that is 2 pi r, and there would be two surfaces. There'd be an inside surface and an outside surface. And so let me just point out, there's how we're going to do the surface tension. The surface tension is a number that tells me how much force I get per unit length per surface. So I need to multiply by the length and the number of surfaces. And then, of course, a pi would cancel on each side. An r would cancel on each side. And we get something very useful in the world of biology, and that is, what is the pressure inside of a bubble? Now, I did a full bubble, and we'll look at some things that maybe aren't a full bubble. But it'll give us an idea that because of the surface tension, this is the pressure. And I want you to notice a couple things. One, not surprising that the pressure depends upon what is holding it together, the material, whether it's a bubble made out of water, or a bubble made out of soap, or a bubble made out of any other fluid, gasoline, whatever. That's the obvious. But the thing that's not so obvious is the radius. What would small radius mean? Big pressure. See how the radius is downstairs? You ever blow up a balloon? What's the hardest part of blowing up a balloon? It's the first part, when the radius is small. Right here. Right there. That's where the pressure is the greatest. Once you get it big, it's easy to blow up. I know when my kids were young and they wanted to blow up the balloons, it was like, Dad, start it for me. So do that, and then they could blow it up the rest of the way. It's the small radius. It's why your author kind of gives this next little picture here and says, what if you took two balloons, or one of a small radius and one of a big radius, and you connected them with this glass contraption with a valve? And so you blow up a balloon and you blow up another balloon, but they don't have the same radius. The one with the smallest radius would have more pressure. And so if you open up the valve here in between, the pressure shoots over. And they're trying to say pressure number 2 is greater than the pressure in number 1. And what ends up is this balloon deflates and that one keeps getting bigger. And it's hard to get two different balloons on the end of this to stay that way, because there's always one that's slightly bigger or slightly smaller than the other, and it forces the pressure in the other direction. And as one gets smaller, its pressure goes up, and as the other one gets bigger, its pressure goes down. So it just keeps pushing the fluid, in this case air, to the other side. Now, your author uses this as a great example of the lungs, because in your lungs, you've got a bunch of little air sacs. Alveoli? Is that how you pronounce it? Yeah, that's how you pronounce it. You want to hear something kind of silly? I think the thing that turned me off as a young student to biology, I really liked it, but there were just so many words, and I couldn't pronounce them and I couldn't spell them. And it was too overwhelming for me. I go, okay, well, life science isn't for me. Let me go tinker with something else here. Anyways, but in the lungs, you've got these little tiny pockets, but to fill them up would take a lot of pressure. And so most of the time, you just breathe and don't think much of it. You don't really fill up the little tiny pockets. That's why it is so healthy once in a while to just go. That big, deep, high-pressured breath. And fill up those lungs. And fill up all the alveoli. Yeah, that word. Okay. And fill them up. Of course, the other neat thing about it is it naturally lets you exhale. And so without much effort, once the air gets into your lungs, you just go, and it wants to come out on its own.
So if nature was the opposite, and so the R was on top, then it'd be almost impossible to breathe, because then, I'm saying like if big radiuses had more pressure than small radius.
So I guess it would be the opposite. It would be easy to get the air in, but harder to get it out.
That's how frog breathes.
Oh, really?
It's a positive pressure breathing.
Oh, okay. Well, and then I'm going to encourage you guys to read this detail. I'm the wrong one to teach it to you. I would assume you get this in your biology class. But because this can get so strenuous, nature has an answer for it. There's these crazy protein compounds, surfactants, that work so much different than what I'm used to, like detergents and waters. Their surface tension varies with their size. And so as they stretch, or as the lung stretches here, and you can see here, as the surface area gets bigger, the surface tension gets bigger. And so this is not a constant number, but it plays along with here, and so this almost remains a constant. And that's then how nature then allows to say, well, you don't have to really have a lot of pressure to fill them out. We can throw in these weird compounds that allow for this effect. And so you can get it deep into the lungs. And that's fascinating, the way the lung works. In fact, there's many diseases with the lungs, and one that comes to my mind is emphysema. And again, it's that part that makes the little chambers disappear. And so if these deteriorate, then you're going to have a hard time getting that air out. And that's why if you know somebody with emphysema, my neighbor's this way, they go to the doctor, and that's the first test they give her. They put her on a breathing machine, and they got to test how hard can she breathe out. And it's not very hard. And she doesn't have the help of the small little bubbles anymore. They've been eaten away, and she's just got one, big one, which also lowers the surface area for absorbing the oxygen here. And so that's, like I said, very interesting in terms of biology, but we better keep going here from our soap bubbles here. All right, so let me look at the next thing, the cohesion, and I think I showed you. Yeah. All right. And so let's look at the cohesion, and maybe I'll stop on this picture because the adhesion is because now let's look at what happens when these molecules hook not to each other, but to the container of it. And your author starts off by saying, let's look at a water that is put on a waxed surface. You probably call this beads, right? If you ever put water on a nice waxed surface, like the hood of a car, when it's well polished, you see it bead up. And basically, the reason that happens is the water would much rather grab to itself, the cohesion, but the adhesion's pretty weak. It doesn't want to hook to that wax. And so you can kind of see this blob build up. But with paint, so if you don't have any wax on that, and a cheapy paint without a gloss coat on it, so just regular paint, the adhesion between the water and the paint is pretty strong. It's even stronger than the cohesion. And so what ends up happening is something that looks like this, where the water molecules grab onto the paint and they then spread out kind of flat and just kind of make a wet surface. And so you don't get the beading effect, you just get a wet surface. And so you can tell when there is a wax or just paint because of that shape there. And so if we then apply that thinking to a tube, a capillary tube, if you will, and that's kind of what this crazy configuration is. I've got some fluids in here. Sadly, I also have a dirty capillary tube, so we won't look at that last one here. But this water wants to stick to the glass. And as it wants to stick, and so it's kind of this picture, it makes kind of this U-shaped, a meniscus. It kind of climbs up the walls. It kind of adheres to the sides of it. Now, other materials don't like to grab onto glass. Mercury is a good example of that. So mercury then will actually then bow kind of the opposite and push down. And it's this bowing effect here and clinging to the walls that makes it climb. And so it's going to climb up the tube, and so we call this a capillary effect. And so this big wide one right here kind of shows the surface level, and it does climb up a little bit, but this one is so big and so wide that how much water it would take and the weight of the water to climb up is so much, we could roughly say it doesn't climb. This is a big tube. But as the tubes get narrower, and this, I'll probably show you a picture, you can't really see it, but this narrow tube, it climbs up and it climbs up and it climbs up. And so all these three are higher than the regular water level. The level that it, I would say, should have been if it was only had to do with the pressure and the Archimedes principle that we were dealing with. Instead, it climbs up. And that's the physics of this capillary effect. The next picture, your author, I think, does a better job here by saying, let's go ahead and look, and he's got 1 diameter, 2 diameter, 3 diameter, and 4 diameter, and each diameter is a little smaller, and when you make it smaller, you can pull up to a higher height because there's not much weight, not much water there. In fact, that gives us a chance to do some mathematics here, because what you could then say is it's getting pulled up because of the adhesion, but remember the liquid has to stay together because of the surface tension. And so I guess mathematically it would look something like this. So here's my capillary tube, if you will. Here's my meniscus. Let's say this is the water level on the outside. And the reason it climbed up a height h is because the surface tension right here is kind of pulling up on it. So let me put right here surface tension. Surface tension. And I'm going to assume that the adhesion is stronger than the surface tension. So the thing that breaks eventually is the surface tension. And so if I were to say what's lifting up, I would start with gamma. Right? There's my surface tension. So how much force do I get? Well, let's go all the way around a circle. So that's 2 pi r. So that's the amount pushing up, or I should say pulling up on it. What's pulling down? Well, pulling down, I would say, is the weight of all this fluid. Remember, from Archimedes' principle, we would say that it should have been at the same level. Well, that's what we talked about before the break. But now it goes above that by some distance, h. And that would be the weight of that fluid. So I'm going to put mg. But like we did before, I'm going to replace the weight, or the mass, I should say, with density times volume. And so then I'm going to put the volume as pi r squared times h. And so if I were to ask this question, how high does the fluid go up this capillary tube? I would cancel a pi, I would cancel an r, and I would leave h over here on the right-hand side. And in the numerator, I would get 2 gamma. Oh, I should be careful with the angle. Well, let me finish this. So 2 gamma divided by rho divided by g divided by r. And so this would be a mathematical way of saying how high it goes. Now, I should have pointed out that depending on this angle of the meniscus, there could be a cosine theta. So this would be the total force, and I should have put a cosine theta. I kind of skipped over that because water is so adhesive to glass that this angle is nearly 0, and cosine of 0 is 1. So if we're dealing with water, we don't need that. But other fluids, it's slightly different. And in fact, your author gives you a little chart here, or somewhere, that shows you the different liquids. Oh, so there's the equation we just got. But somewhere in here, well, I don't see it, but somewhere in here. Oh, there it is. I went right by it. And so this is the angle. And so if you look at water and glass, I was saying the meniscus is pretty steep, so it's 0 degrees there. But as we saw in the other picture, the mercury in the glass goes the other direction. And it pushes the fluid down instead of up. And then they give some other ones here. But I think really what we need is the 0 degrees. That we're going to be working with water in glass. But you can then begin to see that how high will it go up a capillary tube is really going to depend on the radius of that capillary tube. Of course, it also depends on what material, so the surface tension also depends on how much the material weighs or density. That kind of all makes sense. But the big factor is that radius. And so that's why the picture I was at was showing the one that goes up the highest is the one with the smallest radius. And so they're showing a small diameter here and it going up 4 centimeters. Where these other ones don't go nearly as high, and you can see this one's about 1 centimeter, and that one's about 2 centimeters as the liquid climbs the wall here, and we have a capillary effect. Well, I'll call it quits to this chapter so we can kind of get started on the next one, and just remind you then that this is where you want to study to get ready for the exam. But I want to encourage you guys to go ahead and read for pleasure right here, section 9. there really aren't any equations in there. There's nothing I'm really going to test you on. But it talks about the pressures in the human body. This is what I was saying earlier. And it talks about the pressure in the eyes, and the pressure in the spine, and the pressure in the lungs, and the pressure in the bladder, and the blood pressure. In fact, let me just kind of scroll here to a diagram. Now, here we go. Here is the diagram of the blood system. And so here is the pumping of the heart, and there's that 120 millimeters of mercury I was saying about. This is your blood pressure. This is your systolic pressure when the thing goes. Systolic. I hope I got the big one right. Systolic pressure when it pumps, and that's the high one, and that's coming from your left part of your heart here. And so as it goes through, of course, the pressure drops. Then it goes into the capillaries here, and then drops some more, down to 15 by the time it gets into the veins, and eventually makes it back over here to the right side of the heart, where the right side gives it a little pressure, not much, just enough so it can flow through the lungs and reoxygenate, and then get the big pump and go through the body here. But that you probably know far better than me, but it's an interesting read of the different pressures. The pressure in your eye, the pressure in your lungs, the pressure in your bladder, the pressure in your skeleton structure, and so forth and so on. So I'll again leave that as a chance to encourage you to read that, and you can hopefully get a little more excited. I know that one thing life science students don't get too excited about is that they have to take physics. So, no, don't make me take physics. No. But it's so important, at least the way I see it, of how the things work. And in fact, I think you saw that with the torque. So we talked about the bicep muscle and, the lifting and all of the difference between an endoskeleton and an exoskeleton. And of course, now you see it a lot with the pressures.